Welcome, and thanks for attending this presentation. In this presentation, we will explain a video delivery platform that brings operator-grade lean-back TV experiences using OTT streaming technologies. So that means a TV experience with the same quality, the same channel change times, the same latencies as broadcast TV, but all of that over the internet. Before diving into the solution itself, let us first ask the question, do we need this? Do we need such a broadcast TV experience over OTT infrastructures? And what do we need exactly? Well, to answer that question, let us have a look at what viewers really want. How do they want to consume video? Well, we know that changed a lot over the last years. Before, traditional linear TV was largely dominant, but now we see that viewers are watching video on a very wide range of devices and platforms. And audiences today are no longer satisfied with linear viewing alone. They complement that with time-shifted viewing with VOD. And for OTT, well, the quality of experiences that users want are increasingly the same as for traditional TV. Viewers want the same video quality, the same zapping and startup times, the same low latency. And viewers have an ample choice, so all video suppliers and TV operators really need to address this need for quality of experience and large device support, because there are a large number of alternatives easily available. Now, operators wanting to offer a TV-like service, well, they need an OTT solution that, simply said, is as good as broadcast to make their service appealing. Now, what does that mean? That means an OTT solution, of course, that works over all networks and all devices, that offers a very high video quality, that offers low latency and fast zapping, and that offers this lean-back user experience, where really you can enjoy TV, where you can enjoy video viewing as if you were sitting in front of a traditional TV set. The key element in such a solution is the streaming protocol. The streaming protocol has a very large impact on latency and zapping times. So we need a streaming protocol that makes video distribution over IP as good as broadcast. And actually not only in terms of latency or in terms of zapping, but of course it should efficiently work on managed and unmanaged networks. It must scale cost efficiently from a single viewer to millions of viewers. And it must support network resource optimization, unicast with adaptive bitrate, multicast, and a seamless transition between both. There are very good protocols available today. I mean, protocols that are extremely well suited for the use case they have been designed for. But unfortunately, they do not meet all the requirements because they only focus on one or some of the needs and not on all. As an example, if we take plain WebRTC, WebRTC focuses on ultra-low latency, and it's really good at ultra-low latency. But it is restricted when it comes to scalability and ABR. If we take Dash and HLS, they are very efficient, very scalable, they work on all devices, they have a very good quality, but as we all know, they suffer from very large latencies. Low latency Dash and low latency HLS improve this latency, but still, in practice, well, we are still in the few seconds range. HESP, the high efficiency protocol, is a new protocol, and that offers low latency, fast zapping, and that at scale. HESP uses HTTP, and so hence it can use efficient CDN-based delivery infrastructures. HESP zapping times and latency are sub-second, so it's clearly better than low latency Dash and low latency HLS in that respect. Now, you probably wonder, how is this possible? Well, the key of HESP is to use existing technologies, but to combine them in a clever way. And we focus on simplicity and focus on what is essential, what is really needed to do what streaming video is supposed to do, that is, bring video as efficiently and as scalable as possible to the viewers. Well, to start, HESP uses a manifest, but an HESP manifest only contains minimal information on the video, such as where it can be found, what qualities there are. That's about it. And that information does not change often, so typically only when a new piece of video arrives, such as an advertisement, or when a new quality or a new audio track is exposed. But it also means that the manifest is not needed to be fetched just before starting playback or in between playback. HTTP is delivered over HTTP 1.1, so it uses chunk transfer encoding, and that at a very granular level. Basically, a chunk is a frame, and that allows for a very low latency. HSP also uses byte range requests, because byte ranges allow us to start at a given position in the video. And as we will see later, well, that's very beneficial to reduce the startup latency and the zapping times. And alternatively, HTTP2 frame-based streaming, of course, could also be used. Now, HSP uses two complementary streams to achieve its result. A first stream is what we call the initialization stream. The initialization stream contains all keyframes. So this stream is not regularly used. It's only used when we start a new stream. And at that moment, we request the most recent image that's available in the initialization stream. And because the initialization stream's images are all keyframes, playback can start immediately. But we know that keyframes are expensive in terms of bandwidth. So we do not want to continue playing out all the following images from the initialization stream, because that would all be keyframes. So that's when a second stream that we have, the continuation stream, kicks in. After this keyframe of the initialization stream, images now are requested from the continuation stream. And a continuation stream is a regularly encoded stream for low latency purposes. So we request the images from the continuation stream, and we do that starting at exactly the right location, of the image that we want to see by using a byte range request. Yeah, this might be pretty abstract at this stage, so let us try to visualize this. So assume that we have an initialization stream with frames capital A1, capital B1, capital C1, and so on. And then at some point in time, a viewer wants to watch the video. The player will then request the most recent initialization frame, let us say capital C1. Next, the player will automatically request all the following images from the corresponding continuation stream, and that at exactly the right location. So in this case, at small d1. And then followed by small e1, small f1, and so on. All following frames are automatically fetched. Now, the protocol details of HSP define how exactly we find this small d1. And by using a byte range request, we can exactly start at position d1 in the continuation stream. Now, of course, for this approach to work, we need to ensure that the small d1 image only references to one previous image. In this case, the capital C1 that is injected. But by configuring the encoder, we can easily achieve that. Now assume that the viewer wants to change channel. So let us say that the viewer wants to see stream 2. The player will then request the most recent initialization frame of the second feed, so capital G2. And after that, the continuation stream takes over again. This brings us to the architecture of such a platform for broadcast TV experiences, but based on online video. First of all, video feeds come in. They are encoded in the required bit rates and qualities. The video feeds are then packaged and possibly archived for later VOD viewing. We need to have a time buffer for pausing for time-shifted viewing of the live content. There will be an advertisement system, and then all the content is offered using an origin server. Now, in case the network is not managed, then the content is streamed traditionally using HTTP over a CDN to a wide range of devices. In case the network supports multicast, then the content should be streamed as multicast feeds. And then, depending on the device's network capabilities, the client device could either natively consume the multicast, or, which is more likely, we need to use a gateway to convert the multicast into HTTP video streams. But ultimately, exactly the same video feed with the same quality of experience is available on the different client devices. Now, this TV experience platform can run both on-premise and in a virtualized cloud environment. The video feeds simply need to be ingested in the virtualized and/or cloud environment, and then they can be completely operated from there all the way down to each of the individual devices. A first proof of concept implementing parts of this architecture has been jointly set up by Cinemedia, Fastly and TIA Technologies. An SRT input is required. The SRT feeds are sent to the Cinemedia cloud for transcoding and for packaging. The HSP streams are then distributed over the Fastly CDN into TIA Player, and TIA Player will play back the HSP video feeds on the client device. To facilitate the testing, we have set up this trial with the player embedded in a web page with possibilities to control the video playback and to change the channel, either via a button or via keystrokes. A first set of tests we have done is measuring the zapping time for a complete system, that is over the CDN with audio and with video. Zapping time is the time it takes to change from one channel to another, and we measure this by measuring the time between the moment that the viewer presses a button to indicate that he wants to change channel and the moment that this new channel is being played back. Now, we measured an average zapping time of about 330 milliseconds for the specific setup that we have. Now, this zapping time is dependent on the network conditions and depending on the bitrate of the audio and the video. Now, 330 milliseconds is already pretty fast, but we know that we can further reduce the zapping time, amongst others, by optimizing the request scheduling. Now, as can be expected and as we can see from this graph, there is some variation in the zapping time. And this variation is caused by network variations, it's caused by differences in the actual size of the images and the audio frames to be fetched. And you also see that there are some outliers. Now, we identified these outliers to be caused by network issues such as congestion, but also because of other activities on the playback device. The zapping time largely depends on the size of the image and audio frames and on the network conditions. We have measured zapping times over different networks. And not surprisingly, what we see is that the slower the network, the slower the zapping, and the more jitter in the network, the more variation in the zapping times. So starting at the left-hand side, the test that we have done, in an office network, we see that the zapping times are really very low. If we move to a residential network, we see that the zapping times slightly increase. Over a cellular network, where the round-trip times are larger, we see that the zapping times further increase. And if there is more jitter in the network, the variation on the zapping times becomes larger. And then finally, if we really have a long distance between the origin or the CDN edge and the playback device, then of course the zapping times become larger. We also measured the latency. Now, for broadcasters, the important value is the protocol latency. That's the latency measured between the output of the transcoder and the playback device. This latency is important because it gives the time difference between playback using OTT video and playback using traditional broadcast. And we don't want this time difference to be too large. Now, what we measure on this proof of concept setup is a latency between half a second and 700 milliseconds. Of course, this depends on the network in between. The better the network, the shorter this latency will be. For a true glass-to-glass latency, we need to add the transcoding time. And for ultra-low latency, a suited encoder or encoding settings must be selected. Most of the tests that we have done for this ultra-low glass-to-glass latency were with encoding times of about 100 to 150 milliseconds, and that gave a very good balance between latency and quality. And we then reach latencies, glass-to-glass latencies, between half a second and a second. Of course, the latency always depends on the network behavior. Last but not least, we tested how synchronous the delivery is. Synchronous delivery is important because you do not want your neighbors to see live events first. And also, it allows new features like watch parties, where several people watch the same video really simultaneously. And it allows for multi-view applications, where multiple video feeds of the same event can be watched synchronously. An example would be the playback of different cameras of a sports game. Now, we tested synchronous delivery by delivering the same stream to two different devices over two different networks. In this case, residential Ethernet and a cellular connection. And then, by comparing a burned-in timecode, we can see that synchronization is possible up to plus or minus 1 frame. With HSP, as with other protocols, the target latency is a parameter of the player. The player will adjust its buffer, within reasonable limits of course, to achieve this target latency. Now, the target latency has a large impact on the synchronous delivery. The larger the target latency, the more headroom there is to compensate for possible network variations and other variations and to still be synchronous in the delivery. We have done some tests over a residential network and admitted it's a good network. And what we see is that if we set a 500 millisecond latency, then we are synchronous within plus or minus 1 frame. When we set the latency to 300 milliseconds, then we see that the delivery is synchronous within 4 frames. Now, for 25 frames per second system, this still gives a perfectly synchronous perception. We have reached the end of this short presentation. So now it's time to wrap up with a conclusion. We have shown an online video system that's capable of bringing a typical broadcast TV experience with the same quality of experience that viewers are used to with broadcast TV, but now over the internet. The High Efficiency Streaming Protocol, HSP, is a key element of this system. HSP allows for ultra-low latency, fast tapping at scale, and all of that using existing HTTP streaming infrastructures. A trial setup is up and running with components from Theo Technologies, Cinemedia, and Fastly. The HSP player from Theo Technologies, the server infrastructure from Cinemedia with an HSP packager and origin, and the Fastly CDN. Test results are very promising, with sub-second latencies and zapping times, and this with a full system, cloud packager, CDN, player, and in real network conditions. Thank you for listening. In case you have questions, do not hesitate to post your questions or to reach out to us. You can find our contact details on this slide.